Okay, then let's start this lesson about stresses. As you know, we have covered until now several topics during the first semester. Basically, we have learned how to calculate reactions, bending moments, and shear forces, and in some cases, some axial forces for cantilever beams and simply supported beams. So after that, we have learned as well to evaluate or to calculate the geometrical properties of the cross-section of those beams. For example, we have been working with moment of inertia for I sections, rectangular hollow sections, angular sections, channel sections, and you can continue studying the moment of inertia for these cross sections independently of the shape of the cross section. But after the determination of these geometrical properties, the next step in this module will be to evaluate what is the distribution of stresses on those cross sections. So today the idea is to introduce stresses. So we are going to do it in a general way first, and after we are going to study in particular specific problems with numbers. But as usual, we're going to start with a sort of theoretical introduction of what exactly means when we talk about stresses. So in the first place, we are going to introduce what we call as an axial stress. So this is the simplest definition of a stress you can find in any book or in any note regarding structural analysis. So let's say these two rectangles you can see on the screen represent structures. So super simple structures. They can be beams, for example. We don't know if these beams are simply supported or they are cantilever or they have any other restriction. For the moment, yeah, they are just beams in this two-dimensional space. If we apply forces to these beams, but forces that are aligned with the length of the beam, so we are not applying forces as usual in beams perpendicular to the direction of the beam itself, the length of the beam or the span of the beam. In this case, we are applying forces, longitudinal forces are called, in the direction of the length of the structure, this beam in this case. So we have two possibilities. We have the possibility of compressing the beam, as you can see in the first figure on top, or we can pull and try to extend the dimension of these beams, as you can see at the bottom of the screen. So in these two scenarios, the deformation we expect to see is that in the first place, on top of the screen, you have shortened the beam because you are applying forces that are producing this deformation. And at the same time, you see that there is an expansion in the perpendicular direction of the forces. This is because an effect that you know already, because we have mentioned this, is called Poisson effects. So when you have an isotropic elastic material, that is the type of material we are going to use in this module, when you shorten in one direction, you expand in the other direction. When you extend in one direction, you shorten in the other direction. And this is what you see in the second figure at the bottom of the screen. So when you pull the beam, you extend the beam, so you increase the length of the beam because the forces acting in the way that are acting, and you shorten the perpendicular in the perpendicular direction of the beam because the Poisson effects. In the first place, we say that we are compressing the beam, or we are compressing the structures, because this could be a beam, but could be a column as well. In this case, a beam because it's an horizontal structure. So with the bigger length in the horizontal direction. But if you rotate this structure, you can say that this rectangle represents a column, for example. So, but what is important in here is that when we compress, when we shorten the elements, the structural elements, we say that this is compression. And this compression have a negative sign in our convention. So we are going to say that anytime we have compression, this compression will be expressed in with a number, with an unit, for example, in kilonewtons. And this compression will be negative because it's what we have decided to do by convention. But because we are talking about stresses in here, what I said before, the forces in kilonewtons, have to be transformed in a quantity that is represented in unit of stresses. So if we consider the area of this of the cross section of this element, it is a structural element, and we consider the forces acting on the elements in the direction that are shown on the screen, we are going to see that these stresses will be expressed, for example, in Newton per square millimeters, or in kilonewtons per square meters, or in pascals, or bars, or whatever is the unit you want to use for the stresses. But the important thing to remember is that the distribution of this stress on the cross section of our structure will be uniform, as you can see on the screen in this scheme that represents the distribution of the stresses. So it looks like a UDL, but it's not a UDL. This, in this case, is a distribution of the stresses on a cross section of this element that is under compression. The value of this stress will be simply the value of the force divided by the area of the cross section. And we will consider, or we will assume, that this distribution is the same in every single cross section of these elements. Because remember that any element, any structure, any beam, or any column will have infinite number of cross sections, one next to each other. And on these cross sections, the distribution of the stresses will be uniform then, and equal to the force divided by the area of the cross section. The same thing will happen with axial stress. So the forces that are pulling the structure will produce as well a distribution, a uniformly distribution of the stresses, as you can see on the screen. And it will be the same in every cross section, and it will equal as well to the force divided by the area of this structural element. So these are the simplest way of defining axial stresses that can be compressive stresses or can be tensile stresses. In order for us to have this uniform distribution and the same distribution in every single cross section of the beams or of the structures, it's important to remember that we need to keep the loads aligned with the neutral axis, and remember that the neutral axis is an axis that is defined by all the centroids of the cross sections of these structural elements. So this line in here is passing through the center of every single cross section for this beam, for example, and the same thing for the second beam. The reason is that if you have an eccentricity of these forces regarding this neutral axis, this eccentricity will produce some sort of rotations on your structure. And if you produce rotation and deformation, you will produce a bending effect. And this is not what we want to produce in this case, because we are defining only axial stresses. So this is a condition, and then for having exclusively axial compression and to have this uniform distribution of the stresses on the cross section of the structure. As you see, you can, in this case, we didn't define any restriction in these beams, because there are a couple of more assumptions we are doing here. So we are considering in this explanation that the self-weight of the structure is equal to 0. So there is no possibility of displacements in the vertical direction. And one of these forces will be an action and the other will be a reaction, because we want to keep the structure in equilibrium in the horizontal direction as well. And as I mentioned before, because the forces are exactly aligned with the neutral axis, we are not producing any sort of rotation on the structure or bending effect. So we don't need to prevent the rotation actually, because there won't be any rotation and there won't be any displacement in the vertical direction because there is no weight. So the only actions and reactions that appear in these structures are these two forces you can see on the screen. We do this because we want to define precisely what is an axial stress, in this case, compression and tensile stresses. There are other types of stresses as well. It's not only axial stresses, of course. So if we have two more beams on the screen now, so and we have a typically, a typical simply supported beam, and we have forces applied to the beam. Of course, we are going to have reactions. So the actions will be usually the actions on top of the beam, and the reaction will be these two forces that react against the actions. So this beam will be in equilibrium, and we say that it's simply supported just to simplify the explanation. And when you apply these forces and you have these restrictions in here and you produce these reactions, the deformation you expect to have, and this is the deformation because you can see it easily in a test, or because you have a study before the simple supported beam, you expect the beam to bend in the way that the figure shows on the screen. So you see now that that this beam as well have infinite number of cross sections. So, but there is a particularity in here, because when you bend a beam, you don't have any more this configuration as in an axial stress. So you are not deforming in this way the beam anymore. So you are not shortening the beam uniformly, or you are not extending the beam uniformly. But what you are doing is you are bending the beam, producing rotations in the cross sections. So these cross sections at the stream are the cross section that rotate the most. So you can intuitively understand as well, or seeing here on the figure, that you have shortened the fibers on top of the beam, because this length in here will be shorter than the original one, as you can see. And at the bottom, you are extending the fibers. So intuitively, you can see that in the bending process, there is a more complex behavior in terms of the, let's say, the displacements of or the movements of the cross sections, producing this combined effect of compression and tension at the same time. And this is the basic difference between axial stresses and bending stresses. Because in this case, for example, what happened is the neutral axis is not straight anymore. So there is a curved neutral axis in this case. And you see that from the neutral axis and to the top of the cross section in the middle of this beam, there will be a linear distribution of compressive stresses. So you will start with 0 at the exact point of the neutral axis, and you will increase linearly the value of the stress until you reach the maximum in the fiber, in the farthest fiber of this beam on top in here, as I'm showing on the screen. The same thing happened with the tensile stresses. So the tensile stresses will be 0 on the neutral axis and will increase linearly until reach a maximum at the bottom of the beam in this cross section in the middle of the beam, for example. The same thing will happen in every cross section, actually, with different values depending on the values on the internal forces, so the bending moments. But this is the reason why this axis is called neutral axis, actually, because in bending, on the neutral axis, you always have 0 stress. So there is no stress on this neutral axis. So the stress is neutral in there. And you increase the value of this stress, or the stress is increased from this neutral axis to the maximum at the edges of the cross section on any beam subjected to external forces. So this is what we call, if you remember, we have defined the bending moment. So there are the moments internally you can calculate in a beam. And these bending moments are the moments that produce these bending stresses. And in here, you can see as well that a few of the cross sections you can have in a beam, and you see clearly that In this case, this cross-section in the stream is the one that rotated the most. And this is in the middle is the one that didn't rotate because in this case, the loads and the beam they are both symmetric. In this position in the middle, you will have as well another particularity, which is that the stresses will be maximum because you will have the maximum values of moments in a simple supported beam. We are going to see in examples, and it will be more clear. But another thing that happened in a bending process, in a beam that is under, bending effect, is that at the same time you have bending, you notice that these two forces, for example, are tending to produce not only a rotation of the cross sections, but a displacement of the cross sections, a relative displacement of the cross section in the vertical direction, producing a shear effect that we have studied before during the first semester. So if we isolate this area of the beam, we notice that the reaction plus the actions try to move, let's say, relatively these cross sections one against the other in the vertical direction, producing this effect that we call shear stress. And the shear stress has a particularity again, is a stress that is distributed on the cross section depending on the shape of the cross section. But in order to keep it simple for now, we are going to imagine that the cross section of this beam is rectangular. So in this case, the distribution will be a parabolic distribution of the stresses. So the maximum stresses will be in the middle of the cross section. And this is essentially different if you compare with the bending stress, because in the bending stress, the maximums are in the extreme of the cross sections. But in the shear stress, the maximum is in the middle of the cross section. So this will have implications in our decisions regarding the design or the checking of any structure in the future. So this is what we call shear stress. And of course, the bending stress and the shear stress have conventions in terms of signs. So we have bending stresses that are positive, the ones that produce tensile effects, let's say, and compressive sign when they compress the fibers. And the shear stresses follow the same convention as the shear forces. So these scheming here represent a positive shear stress. If you have the opposite, you will have a negative shear stress. And the same thing for bending. This deformation in this way, producing tensile stresses at the bottom of the beam, is what we call a bending moment, a positive bending moment. The opposite, as for example in a cantilever beam, is going to be a negative bending moment and a negative bending stress as well. But as you see, the bending stress is actually positive or negative at the same time, because we have this linear variation of the stress. So in this case, for example, for this beam that is under bending effect, you have an area with positive bending stresses and an area with negative bending stresses. If you have a cantilever beam, you will have the opposite. So the compression will be at the bottom and the tension will be on top. This is the difference between the bending effect on a simple supported beam and a cantilever beam. And in more complex structures, you will have a combination of these behaviors, of course. So you need to determine the sign of the stresses in every case. So something to understand is that then the effect of bending and shear stresses in a beam acts together. So they are not isolated. There are cases where you can have some pure bending stress or pure shear stresses, but you need to design in a particular way the structure and apply the forces in a particular way as well to isolate the effect. In general, if you try to remember the distribution of the bending stresses and the shear stresses on beams, if you remember they act together, let's say. So it's difficult to separate the effects of bending stress and shear stresses in a beam. But if you design the beam in a particular way, you can do it. We can discuss this in a on-campus in the next lecture. So, but this is the definition then. We have defined 4 types of stresses. We have defined actually 3 only. The axial stresses that can be compression or tension. You have the bending stresses and you have the shear stresses. In here, there is a kind of resume of all the possibilities. So when we talk about axial stresses, then again, these can be tensile stresses or compressive stresses. So in the scheme, you see only the tensile one, because the compressive, it will be the same, but with the forces in the opposite direction. And the distribution is uniform, as you can see on this diagram in here. You can have bending stresses that produce a combination of tensile and compressive stresses at the same time with a linear distribution of these stresses. You can have the shear stress as well, that is represented in this way. And remember that usually it's produced in combination when you bend a beam. And the distribution of the stresses is like this, so there is not a volume of the stresses, because the shear stresses act on the cross section directly in the same direction, differently to the axial stresses and bending stresses that act perpendicularly to the cross section. And there is another shear stress, or another source of shear stresses, that is the torsion, which is a 3-dimensional effect in an structure, so you cannot study this in 2 dimensions. But the torsion as well produces a sort of shear stresses on the cross-section that are distributed in the same direction of the cross-section, but they are distributed in a different way. So they don't have a parabolic distribution, they have a linear distribution that we will study at the end of the course, hopefully. But the shear stresses produced because you have a bend, you are bending a beam, or because you are producing a torsion on an axis, for example, or they are both shear stresses because they act on the surface of the cross section. So there are a difference between these axial stresses and bending stresses that act perpendicular to the cross section, and these shear stresses that act on the surface of the cross section itself. Just in order to connect this topic of stresses, all the stresses we are going to study in this module, with the internal forces we calculated before, it's a good idea to have this exercise with numbers to resolve the whole set of the stresses for this particular beam. And for a particular cross section, we are going to study more of this. So don't expect to understand every single detail of this example, but it's just to link all the topic we have been studying before. So in this particular beam, this cantilever beam, as you can see, there are forces acting in the vertical direction, but I added as well this 15 kilonewtons on the extreme on purpose to have some compressive forces on the cross sections and to see how we calculate the compressive stresses as well. So as usual, the first thing we need to calculate when we have a beam, this cantilever beam, for example, is to calculate the values of the reactions. So in order to do that, what we are going to do is to use the usual summation of moments around the point A, where you have applied the fixed support, and summation of forces in the horizontal and vertical direction. And doing that, we are going to work out the values of these reactions. In the horizontal direction is 15 kilonewtons, canceling the horizontal action of 50 kilonewtons in the right extreme of the beam. We are going to have a vertical reaction of 50 kilonewtons on the fixed supports, because the external vertical action of 3 kilonewtons per meter and 20 kilonewtons. And we are going to have a moment of 105 kilonewtons that is a reaction at the point A because of the fixed supports that is produced by the external moment produced by the UDL, the 20 kilonewtons, and the 20 kilonewtons you have applied on the beam. So you can work out this by yourselves to check if this is right. after the calculation of these reactions, so what we do is usually is to produce the shear force diagrams and the bending moment diagrams. And in this case, because we have these 15 kilonewtons on the extreme, the right extreme of the beam, we are going to produce as well an axial force diagram. So I'm not going to explain the details of these diagrams because this is part of other lectures and topics. But at the end, after the calculation of this diagram, you see that the distribution of the shear force is linear, with a maximum in the left extreme of the beam of 50 kilonewtons of shear force. The distribution of the moments is clearly parabolic, and need to be parabolic because remember that the shear force is the derivative of the moment, so this has to be parabolic distribution. The maximum moment we have is negative and is equal to 105 kilonewton per meter. And the axial force is just a compression produced by 15 kilonewtons in the right extreme and the reaction 15 kilonewtons to the left. And it's uniform because there is no any other axial effect on this beam along the span of the beam. So in here we see the how useful it is to have all the diagrams together aligned with the structure, because now we are able to identify the values of the shear forces, the bending moments, and the axial forces in every cross section. For example, if we want to see what's happened at the cross section 1, we have 35 kilonewton of shear force, and we have minus 41.25 kilonewtons per meter of bending moment, and we have minus 15 kilonewton of axial forces. So we have the information of the internal forces for every single cross section. And this is very useful when you have to calculate the stresses on the cross section. So let's say that this cross section of this cantilever beam is a rectangular cross section. So what we know a priori in terms of the shear stresses is that the shear stresses have a distribution, a parabolic distribution, as you can see on the screen. And we need to determine the value of the maximum shear stress in here in the middle. Because if we know that the shear stress is 0 in these two extremes, and we determine the maximum value in correspondence with the neutral axis, we are going to be able to sketch or to draw this parabolic distribution, because a parabolic distribution is defined with 3 points, if you remember from math. So the shear stresses will be produced by the shear forces. This is another connection you need to make and you need to understand. So if we want to calculate the maximum shear stress in the middle of this cross section, we need to establish where is the maximum shear force in the first place. And in the diagram is clearly 50 kilonewtons. When we talk about the distribution of bending stresses, we know now, because the definition, that in a cantilever beam, because the cantilever beam will try to deform in this way, you will have tensile stresses, tensile bending stresses on top, and compressive stresses at the bottom, with the maximums at the extreme of the cross section. And in order to calculate the maximum bending stresses for this beam, you need to identify first where is the cross section with the maximum bending moments, because the bending moments are the ones that produce the bending stresses. So in the diagram, clearly the maximum is 105 negative moment that will produce the maximum shear, the maximum bending stresses, sorry. So again, there is a link between these two definitions, these two elements, so the bending moments and the bending stresses. Finally, if we want to establish the values of the axial stresses that are uniform along a cross section, we need to identify which is the maximum axial force. And in this case, the axial force is constant along every single cross section of the beam. So any cross section will be valid to calculate the maximum axial force and axial stress, and will be a compressive stress in this case. So I have located very clearly the neutral axis in here to to try to have a scheme that explains in every single detail what is going on with this cantilever beam. I will work with newtons per square millimeter because this is the usual unit we prefer to use when we work with the stresses, just because it's a appropriate units if you consider the values that we usually manage in structures. And again, this is the most important thing to connect today in this lesson. Shear forces produce shear stresses, bending moment produce bending stresses, and axial forces produce axial stresses. So if we give some values to this exercise in terms of dimension of the cross section, let's say the cross section is 20 millimeters width and 50 millimeters height. So now we can calculate the area. The area will be 1,000 millimeters squares, and the moment of inertia will be the base 20 times the height 50 cubed divided by 12. So this will be the value of the moment of inertia, 208,333 millimeters to the 4. Now you will see why we have calculated this moment of inertia and when we use it to establish values of stresses. So in order to calculate the maximum shear stress, we need first to know that the maximum will be in correspondence with the neutral axis. So we are interested in defining the area in green, you can see on the screen, that is on top of this neutral axis. And we need to be able to locate the center of this green area that is on top of the neutral axis as well, because we need the distance from this centroid to the neutral axis. And this is because in the formula we are going to use to calculate the maximum shear stress will be the maximum shear force, which is 50 kilonewtons or 50,000 newtons in newtons. We need to calculate something called moment of area, Sx, which is basically the area of the green rectangle on top of the neutral axis multiplied by the distance from the centroid to the neutral axis, divided by the moment of inertia we have calculated before, times b. B is the width of the cross section in the location where we are calculating the shear force, and in this case is 20 millimeters. So the maximum shear stress for this particular beam and for this particular cross section is equal to 75 newtons per square millimeters. So now we know not only the distribution of the shear stress produced by the shear forces, but we know the value as well of the maximum shear stress, as you can see on the screen. In order to calculate the maximum bending stress, we need to apply this other formula here, which would be tensile or compression. The maximum moment, that is 105 kilonewton per meter. That's, if you pass to Newton per millimeter, will be 105 millions of Newton per millimeters, divided by the moment of inertia, and this moment of inertia need to be divided as well by a quantity, which is the distance from the neutral axis to the fiber where you want to calculate the stress. And in this case, because it's the maximum, we want to calculate the stress in this extreme on top or in this extreme at the bottom, so the distance is 25 millimeters. Doing the calculations, you found the value, and now you have not only the distribution of the bending stresses, but the values in corresponding with the neutral axis, which is 0, and the maximums on top, a tensile stress of 12,600 Newton per square millimeters, and the maximum in compression, which is the same value, but negative. As we have defined as well the axial stress, the simplest one is just the axial force divided by the area. So in this case is compression. The maximum compressive force in the beam is 15 kilonewtons, but in Newton is 15,000. Divided the area 1,000 millimeters square, we have calculated the axial stress for this cross section and for this cantilever beam. So this was just a short introduction of what we are going to study in more details during the second semester, actually. because all of this will change depending on the shape of the cross section and depending on the type of beam we are analyzing. So we are going to do this exercise for simple supported beams and for cantilever beams. And we can do the same for trusses, and we can do the same for pre-beam frames as well. So in every structure we study in this module, we need to be able at the end of the module to establish not only the reactions and internal forces, but the stresses as well on the cross section. And doing that, you see that you have every single information about what are the forces and what are the distribution of internal forces and the distribution of the internal stresses that every single cross section suffered. And this is what we call a stress analysis. So this is the reason why we need to learn all of this. So the values we have calculated in here are the maximum because we have chosen to work with the maximums exclusively. But sometimes we want to calculate the, the distribution of stresses in other locations. For example, if we want to do the same exercise regarding the cross section 1, for example, the one that is in here, we are going to use the values of the shear forces, bending moments, and axial forces to establish the distribution of the shear stresses, bending stresses, and axial stresses. Of course, in this cantilever beam, all the cross section have the same area. In some cases, it's not the case. In some cases, beams change the cross sections. If you remember, at the beginning of the semester, I have introduced something called delta beam. A delta beam have cross section that have a variation in the length of the beam, but in this case it's uniform, so the moment of inertia will be the same and the area will be the same. So you have the values in there and you calculate by your own the values of this distribution of the stresses at the cross section 1, for example. But you notice that when you have the diagrams, you notice that there is values of shear forces from the section A to the section 2 in green, and from 2 in blue and until the end of the beam there is no any shear force. And because there is not any shear force, there is no any moment neither, because if this is 0, so the derivative 0 is only for a constant value of bending moments. The bending moments in this case is 0, so the derivative is 0 as well. So this in this area from the middle of this beam until the end to the right, there is no shear forces and there is no bending moments, and this will have let's say an impact on the distribution of the stresses, of course. For example, if we check the stresses at the section 2 in green, in there we have 20 kilonewton of shear force, but we have no bending moment. So this is the reason why the bending stresses are equal to 0. But you have shear stresses and you have axial stresses because the axial internal forces are constant along the whole beam. If you go to the cross section 2 prime, just after the force of 20 kilonewtons, you see that in there is no shear force, so there is no bending moment. There is only axial forces. This is the reason why these two shear stresses and bending stresses are equal to 0. And you only have from the cross section 2 prime until the end of the beam, only axial stresses of minus 15 Newton per square millimeter. So you see now altogether the reason why we have been calculating reactions, the reason why we have established and sketched this diagram of bending moments, shear forces, and axial forces, and now you will be able to calculate the values and the distribution of the shear stresses, bending stresses, and axial stresses on any beam. So this is the introduction of stresses. Then I will stop now the recording.